Hi, it's Stockton Maxwell from the Department of Geospatial Science at Radford University, and today I'm going to go over principal components regression using the program PCreg, initially programmed by Ed Cook and I believe Paul Krusik from the Lamont Tree Ring Lab at Columbia University. And so I want to make sure that you all have a good understanding of how to work through the program to create reconstructions. This methodology is kind of the backbone for the North American Drought Atlas, and so it will give you a good understanding of how to do climate reconstructions using tree rings. But you may want to modify these procedures for your purposes, including other estimates of uncertainty. But let's go ahead and have a look at it. You can download the PCreg program from the Lamont Tree Ring site. They have a software tab. You can go and pull it down. It's also where you would get RStan, Cophacia, and some other the tree ring programs. You'll see on my screen here that I have the zip folder. And if you look in that zip folder, you will see that it comes with 2 applications and a couple of example data sets. I already have it unzipped and I have run through it once, but I'm going to go through and show you the format of the files that you need to put in there and some of the settings that you need to make sure that you have correct for your reconstructions to come out appropriately. So let's start out with look at the data types. So we need sets of detrended chronologies to begin with, and so I have a file here. And the example that I'm going to be using is for a project that I'm working on with Grant Harley and others out in Wyoming, where we're doing hydroclimate reconstructions. This is the Corwin gauge of the Yellowstone River that we're going to be doing a reconstruction on. And so this initial text file that you're looking at here, these are the output chronologies from RStan. This is in that kind of compact format. And if you have a look at just an example chronology here, this is from the Between Two Knobs site in Wyoming. But look at this. This is the output from RStan for one of the Doug fir chronologies. And so we can see we have the transform data set. Here we have the standard chronology. And essentially what you do is you would create a single text file with all of your chronologies in there, stacked one on top of the other. And then you would have a file that looks like this. This would be your input. And so here we have a series of RStan chronologies. We put in chronologies from surrounding states within that climate footprint that has been discussed in some of our research papers. And so here we have chronology after chronology. These are RStan chronologies. Occasionally you'll have RStan standardized chronologies in there. It really depends on you looking at the data and understanding what is being recorded in your tree rings. Is there an actual lag in the instrumental data set? And does that lag carry over into the actual relationship with tree growth? And so this is your first file. You need a chronology file, all of your data stacked in there. It's really just a copy and paste operation from that RStan chronology file. So go ahead and close those out. The next one that you will need is the actual gauge data. And so is that precipitation, Palmer Drought Severity Index, or for us it's going to be Streamflow. And so what I have here is another file. This is the Corwin gauge. And what you're looking at here is a specifically formatted file for PCreg and some of these other programs that use Fortran coding. What you have here is you have the 12 columns representing the monthly flows. And this has been log transformed. We looked at the assessment of normality. It was not normally distributed, so we log transformed it to kind of adhere to regression principles. And so you just need a year column and then those 12. However, if we open this up in Excel, we got to make sure that we're actually saving this correctly. So I can show you how to create this file. And if I just pull in the Corwin data, you can see that it comes in as a formatted text file. This file needs to be saved as a formatted text file. It's a .prn file rather than a .csv or .text file. If we look at this and set it up so it's delimited, this is what it would look like. You can have this top header in there. This is mainly if you're using the PPR regression program, but if you are in PCreg, you can either have this here or not. But what you're going to need to do is you're going to need to make sure that each of these columns has the set width, column width, of 8 spaces. And if it's not, the program may not read it. And so you need to have it set this way. And so highlight all of your columns, set your column width to 8, and it will adjust it. And then you're going to go to File, Save As, and we'll just save this again in the PCreg folder. I already have another copy of it in there. Just call this 2. And instead of tab delimited, we're going to go down and find this one. It says formatted text space delimited, and this will save it as a .prn file. That's the correct format. So we can go save that. And we do want to keep using that format. Close it out. And that's it. And so it should end up looking like that. We can just go and open our example of it. See here it says .prn. And if I open this up with TextPad, you'll see that formatted file in there. Now, so that's important. You need to have a formatted text file. It needs to have columns that are 8 spaces wide, and then saved as formatted text. So once you have your 2 input files, you have your chronologies, and you have your hydroclimate variable or your variable that you would like to reconstruct. Now we can actually start the program. And so there's a couple different versions in here. You can just do the top one here, the ERC2. And this is going to look a lot like running RStan or Cophatia or these other programs. And so it looks like a DOS prompt window. And so I'm going to run you through each of the settings, and then I'll have the output data sets for you to look at later, put up a link for you. And so we're going to go through, and I'll do a brief explanation of each of the options as well. So we could start out, and if we've run this before, we could run it from a log file. And this is often what I do after I've run it. I'll just go to the log file, adjust the parameters in there, and then just read the log file, and then it'll run through the reconstruction. That tends to speed things up than going through each prompt and setting your parameters. But right now, we're going to go from a fresh start and take from there. We could save intermediate output. That can save a bunch, so we're just going to do no. We're in Wyoming, so nothing in the southern hemisphere. We can title this Core Win Test for you all. And we need to enter our predictor file name here. And so our predictors are tree ring chronologies. We have is crons_corewin. So we're going to type that in, and you need to have those files in the same folder. Otherwise, you have to type out the whole file path. It's similar to the RStan program. So crons_corewin.txt. It's going to ask us what the format of that data set will be. And so this is a set of tree ring data, so that's number 2 here. But you could have other types of variables in there. If you were running a gridded reconstruction like the North American Drought Atlas, you can actually have this all set up so you have each individual chronology with its latitude and longitude set. And so we can actually read in data, and so it will send out a search radius and just collect chronologies within, say, a 400-kilometer search radius. Since we're just doing one gauge, we don't have any latitude, longitude data we need to really worry about. We're going to throw in all of our predictors. And so we're going to hit 0 here. And it goes through and it looks for the common period. We could assess whether or not this common period is okay. That's a pretty small common period, so I'm going to adjust it. And based off of looking at the data previously, I'm going to start with, go with no here, and then it's going to ask for the first year, and I'm going to go with 1765. This is just based off of the previous run. And the last year here is going to be 1983. The reason why we're doing that is because you might have some really young chronologies in there, and so that first common period window, you don't want it to be too short. We have some chronologies extending into the 1700s, and of course a lot of the chronologies were collected in the 1980s, and so that gives you good replication, a good sample size for your first nest or your first common period reconstruction there. You can also model that forward in time if you want to the present day. So it's reading in each of our chronologies, gives you a little bit of information It's got the begin year, end year. It's got your species. It's got the little bit of metadata there. You can see all the latitudes and longitudes are all the same. We just forced it all to be the same. And then it's also got the name of the chronology there. Our next option here is if we want to pre-whiten the predictors. And so do we want to model the autocorrelation and remove that autocorrelation for this? We have RStan chronology, so we've done a bit of this already. We've removed the autocorrelation and then put a portion of it, the pooled autocorrelation, back in. So I'm not actually going to pre-whiten, but you could have standardized chronologies here and then pre-whiten if you would like. So no pre-whitening here. Do we want to lag or lead the predictors? And so you might consider this if you want to use the growth in the following year to predict climate in this year. So we know that trees have this lag effect, so the previous year's climate can affect tree growth, and so we can take advantage of that. It does act to build the pool of predictors even larger, but then we will whittle it down using some correlation functions. So let's go ahead and do a lag. Oh, actually, let's not do the lag this time, guys. That's fine. You can do the lag if you want to, and create a mask if you'd like. Maybe I'll run through and show you an example of that, but otherwise it doesn't matter. Now we need our predictan names. We have the Yellowstone Corwin gauge here, and it should be Yellowstone Corwin log.txt. And it should read this in just fine. It's going to ask us for the format of the data here. And so with this data set, this is considered monthly climate data, the way we have it set up. The next thing is going to ask you, do you have latitude and longitude? Well, we don't, so let's put in 0. How many climate data sets do you have? We just have one for our case, but if you had a gridded data set, each grid cell would have climate data to it. And now we need to set up the format, and this is where Fortran comes in. The format of our data set, based off of that formatted text file with the 8-character wide column, is actually open parens I8, 12 F8.0 and close paren. And so we would want to punch that in. Oh, actually, sorry, I need to hit 5 here first and then enter that, because enter our own format for this. So now enter our own format. So open parens here. We need I8 12 F8.0. And this is why you run it from the log file, so you don't just keep having to keep on typing in this stuff. I'll just check it with my previous run, and we are good to go. The next thing we want to do is we want to choose our months here. You can see it's running from January, February, March, April, May. Those are each of the months. And we want to go and put in numbers here for the months we want to reconstruct. And so if we wanted to reconstruct, say, June through October Streamflow, the average Streamflow, we actually have to go through and put in zeros for the months that we don't want, and then put in a 1 for a month that we do want. If we were to do this for JJA 111, it would actually run reconstruction separately for each of those individual months. But if we wanted to look at the average across those months, let's go all the way to October, we would hit in another 1 for September, and then on the O, we hit 3. That means that's a code for the program, and it says, okay, average across these months. If you wanted to actually run individual reconstructions for those individual months, you can. It cranks out a ton of output and reconstruction for each one if it's legit, so just leaving the ones there. But otherwise, if you want to do an average across the time period, which often we do seasonalize things, you would need to add that 3 in the final month of interest. Once we have that climate mask, you can hit enter. Here it's going to look at the common interval here. This is going to be for your calibration verification period. And so From 1911, that's when we have the beginning of our Streamflow gauge data, to 2017. We know that we are stopping our chronologies in 1983, so we probably want to at least adjust that. So let's change our common interval here. We can start out with 1911 for our first year, and the last year will be 1983. Now we could also pre-whiten the predictand, so we could pre-whiten the Streamflow, but since we've already log transformed it, we are fine, and I've already assessed whether or not it has a lot of autocorrelation. It doesn't, so or actually it does. So we do want to pre-whiten, but you want to look at that to see whether or not you should be pre-whitening. But we can go ahead and pre-whiten to remove some of that auto regression. Pre-whiten the predictands. It's going to ask us for the period that we want to estimate that, and so we can just use the same period, 1911 to 1983. And do we want to lag or lead the predictors? We don't want to do that either for this, but I can show you an example with lagging at least the tree rings. But we'll go with no again, keep this model a little bit simpler. Now we got to do calibration, define our calibration verification period. What we're going to do here is we can set it up so we can calibrate on the early part and verify on the later part. And so just doing some quick math there, you get about 70 years of data. And so you just want to split it up roughly 50-50. Some people do 2/3 versus 1/3. Calibrate on 2/3, verify on 1/3. But you can just do approximately half of the data, 50% of the data. And so we'll just go in and say, our first year of calibration will be 1911, and then we'll tack on 40 years there. Let's just round it out to 1950 so I can remember it. 1950 as our last year of calibration. And so we're going to go ahead and choose our method now of reconstruction. And so the method that Ed Cook commonly uses for the North American Drought Atlas and the other atlases in the world that he's worked on, and the way that I do these reconstructions, as well as Grant Harley, my colleague, we use the point-by-point regression. Essentially the way we're functioning right now in this example, though, is just a single point. And so we're going to use 1. We can now set the significance level. And so the reason why we want to do this is that now that we have all of those chronologies in there, we need to screen them for correlation with the actual gauge data. And so what's the level of significance that we're willing to accept? And so if we do a 0.1, that's going to be a little bit more liberal, include a lot of predictors. It may overfit a bit. And then you might just iterate through and look at a sensitivity test of it. So start out with 0.1, go to 0.05, and then maybe 0.01 if you have too many predictors and you need to eliminate a lot. We'll just start out here with a 0.05, 0.05. And then we need to understand, is this a one-tailed or two-tailed hypothesis? And so if we're thinking about Streamflow and the gauges, we should have a positive relationship. And so this is a one-direction, a one-tailed test here. And so increased Streamflow means increased tree growth, right? Now you may not have that in some systems depending on your hydroclimate variable. So for instance, with snowpack, you actually might have both positive and negative relationships depending on the elevation at which the trees grow. And so you could have a two-tailed hypothesis there. For our purposes, we are just going to go with a one-tailed hypothesis, and then we are assuming a positive correlation here. We're hypothesizing that positive correlation. And so that is going to go through and screen our predictors, screen our tree ring chronologies, so only significant tree ring chronologies or chronologies have a significant correlation with the gauge data stay in the model. Next, we are moving into the principal components section here, and we need to identify how we are going to select those principal components, those PCs. And so this has an eigenvalue cutoff criterion. The typical one we use is the Kaiser-Gutman rule. This is the eigenvalue of 1. You can use other methodologies. This one's pretty well justified in the literature. But there may be instances where you want to be a little bit more liberal and have more PCs in there. But that's kind of up to you methodologically. You can choose your own method here, but I'm going to use the Kaiser-Gutman rule. Now, with our regression model criteria here, how do we want to select those PCs as predictors? Now, remember here, the PCs have basically distilled down all of those tree ring chronologies we loaded into time series that are principal components now. And so we are now creating a regression model with PCs instead of the actual tree ring chronologies. And we don't want to just keep on loading in a bunch of principal component predictors. And so to set how a model selection here, we want to have some criteria for stopping the model and assessing the best model. And typically what I use is the minimum AIC criterion, Aic information criterion. You could also use the BIC if you're running this in other programs, or if you're programming it in R for yourself. We'll go ahead and move through with the minimum AIC. Now, you can have long or short output. Initially start with the long output so you can kind of walk yourself through it and see what the black box is doing, and so that you understand the methodology and you understand how the regression is actually created. Otherwise, I wouldn't be comfortable with using the program. So make sure that you're comfortable with it. If you have questions, feel free to email me. Let's go ahead with the long one. So the program's going through right now. It's assessing the predictor's correlation with the Streamflow Gage data. Then it ran the principal components analysis. And so boom, that's one of the beauties of this program, and Ed Cook and Paul Krusek doing the service for the community, is that that's a lot of heavy statistics that I just ran through as the screen was flowing. And so we can look at some of this and see that we had initially all of these predictors, 46 passed our test here. And so they have a significant correlation. And you can see the R values with each of the chronologies. And even it's kind of percent variance explained in terms of how it feeds into the PCs. So that's 46 potential predictors. If we lagged those, there actually might be a fair number more, because we do have some lagged relationships with tree growth and hydroclimate in Yellowstone. Now it's going to run through and it's going to load all of these into a principal components analysis, and it develops this PCs. That first PC, PC1, is now this new time series, it explains 42.7% of the variance of the instrumental of the tree ring data sets. And so there is some commonality there between the tree rings. And so that's all now loaded in, essentially. All that common variance is loaded into PC1. PC2 adds an additional 13.6%, and so on. And then what we want to do is we don't want to take all of those PCs. We want to only take PCs here with this original lambda, where our eigenvalues are greater than 1. So that'll bring us down to PC8. That's going to have 8 predictors retained based off that Kaiser-Gutman rule. But you can see number 9 there is close. If you were to round it, that'd be a 1, but you need to have some criterion for limiting the number of PCs that then go into the stepwise regression model. And so it has gone through and run our first regression. And this is a stepwise regression. It's got now 8 potential predictors. It's going to go through, it's going to put in one of the eigenvectors, one of the PCs. It's going to put in PC1 first. It's going to run the analysis and develop an R-squared value, an adjusted R-squared value. Here, that first PC is predicting 52.9% of the instrumental data set. So that's already a decent model. And so what it's going to do is it's going to calculate adjusted R-squared that will have a penalty for adding in new predictors. And then it also has AIC, which also has a penalty term for adding new predictors. And so this way you just don't have a model that overpredicts or inflates the variance explained because you simply added in extra predictors. And so here it's going to go through, it's going to add in PC7, PC6, and from there, that is our minimum AIC, negative 27.96. At that point, if you add in another predictor, it goes up. and that's where the model stops. And so our best model using minimum AIC, adjusted R-squared, 57.2%, which is pretty good. Now this is just on the calibration period, but if we were to adjust that calibration period, these numbers might change a little bit as well. We're going to go again. I'm going to hit enter here to return. Keep going through. Now it's going to run the verification models. I'll go with the long output again. And in here, it's going to calibrate on our early period. It shows us our data set here. It shows us our first difference in reconstructed data sets. And then as it goes down, we get a little bit of extra information basically on the reconstruction. Here we can see some of our correlation values between our PC predictors and in the chronology. And so we have some really high correlations, Pearson correlation coefficient of 0.778, robust correlation 0.776, and so forth. And it also calculates a couple key verification statistics. That's a reduction of error statistic in addition to the coefficient of efficiency statistic. Now, I'll leave you guys to go through and dig through the explanations of those. But essentially, what happens is with the RE, you're comparing your now predicted hydroclimate data to the average of your calibration period. And so you could just simply use the average and see how that predicts versus your actual reconstruction. And then the coefficient of efficiency does that same thing where it compares your reconstructed data, but now it's comparing it to the average of the verification data set. And that's a little bit harder to pass. So those are two fairly rigorous verification statistics, and they range from negative infinity to positive 1. And essentially anything above 0 indicates that you have better predictive skill than the average of the calibration or verification time period. But when it tends to drop pretty low, you just got to understand that your reconstructions may not be as strong as you would like, so use with caution at that point. I'm going to hit return now to continue through our menu, and now it just has an overview. Well, keep going. Now it just has an overview of our calibration and verification period results here. And so here we have our calibration on our undifferenced data. We can see our Pearson correlation, our robust correlation, and our Spearman correlations. Here we have the RE and CE statistics here, 0.559, 0.559. If you go down to the verification period down here, now we can see our RE and CE statistics. It's verifying, it's above 0, but we are not necessarily explaining as much as we were during the calibration period. And so this model verifies, it's decent, but it is not as consistent across those two time periods. And so this is why we do this split calibration. It's about time stability, and we want to make sure that our statistics are balanced across those two time periods. And so I would run this model calibrating early and verifying late, and then I would go back into the log file and I would actually switch the calibration period. So I'd calibrate on the more recent time period and verify on the early time period. And that way you can see how well your model is doing and how those calibration and verification periods change your statistics. And then ultimately, when you run this reconstruction, you're going to calibrate it on the full period. And so you do the two different models where you calibrate early, verify late, and then flip it, and then you finally calibrate on the full period. So here, 1911 to 1983, that would be the full calibration model that you would then apply and push backwards in time, right? And so the reconstruction is actually finished, and we can look at some of the output data now. And so down here, there's nothing left. We're just going to X this out, and we're not going to save anything. And so now we can look at some of the output. I'll run through some of this. Open it up in TextPad. Initially, our log file here, this is all of the settings that I used to run it. The one thing that I might change would be changing whether or not we're going to lag or lead our predictors there. And I'll run through that here in a second. But then we have our output. this runs through and shows you all of the steps that we just went through and all of the output resulting from each of those steps. So it's going to read in the tree ring chronologies. It's going to identify our common period. It's going to run through the principal components regression, and ultimately it's going to produce our predicted estimated streamflow from the model based off of our calibration and verification periods. And so we can go and run that, and we can look at all of our predicted data in here. You could go and copy and paste some of this out of here, but you would also then potentially just want to go to, we have these two files here, the redden reconstruction. Some of the auto regression is actually put back in. So if we pre-whitened it, the data, we could actually redden it and put some of that persistence back in. If we didn't want to use that, we could use the whitened reconstruction. And so you have a couple different options there. And that's kind of up to you statistically what kind of decisions you'd like to make. Other files we have in here, we have the correlations and betas. The betas are actually helpful because they can tell you the influence an individual chronology has on the model here. And so we can look at this and see the ones with higher beta weights fed in more into the model. And you can actually identify each of those chronologies and see, okay, well, which ones are most important for my reconstruction? So you might use this if you want to update it, or maybe you want to use more chronologies from that particular species or something along those lines. And so we have some statistics here for our calibration and verification for the reddened and the white reconstructions. And that's essentially the output. And so what you would want to do is basically create a spreadsheet. You would paste all of this data in there. And then if you were doing nested reconstructions and changing your common period, here we started in 1765, but if we push it back to 1700, we put it back to 1650, that's going to rerun the model again. And we just basically splice on the results for those nests, those next runs. And as we go back in time, chronologies fall out. And we would basically want to identify each potential time period where a chronology falls out and run that reconstruction, changing that common period to build that nested reconstruction. You could also do it forward in time. And so instead of 1911 to 1983, you could actually go up to, say, 2000 or 2015 or even to 2018 if you have chronologies up there. Just know that the fewer chronologies you have, the likely of variance explained being really high is really not there. So also, again, use with caution. You want to have high replication or high number of predictors for running this. And so that's basically it for PCreg. The one thing that we could do is we could go in and lag our lead, our predictors. And so we could go in and what I'm going to do is I'm going to copy and paste a couple lines in here from another file. And so with lag or lead, the predictors here, if you were to actually hit a Y here and rerun this, it's going to pull up a lag mask. And similar to the way we would do our climate mask down here, you need to put ones in for the lags. And so here you need to think about how you would do your lag, and this is a little bit off the way it was pasted in, the way you would do your lag. And so here it has a 1 in the year 0, and it has a 1 in year +1. The reason why we might want to do this is because precipitation this year actually may have a positive effect on tree growth the next year, right? And so that's a +1 lag. Now, if we were running a climate response function where we're trying to predict tree growth based on climate, that would be a different lag. That would be a -1 lag. So climate in the previous year could predict growth this year. We're flipping that, transferring it, and so now we're using a +1 lag. So tree growth in the following year could predict climate this year, if that makes sense. Now you could do lags for 2 or 3 years as well. You're probably going to inflate the number of chronologies that go in there because every time you add a lag, you're adding a lag for every predictor in the data set. Then it's going to go and screen it with that correlation analysis. So if I save this here and go and rerun PCreg. And I'm going to call up the log file here. And so hit enter, read from a log, yes. And then it's PCreg osx underscore log.txt. And as soon as I hit that, it should run through. Let's see here. And run it. So what did I do here? Got 0 headers. All right, there we go. And so it's just going to run through and do the analysis for us, just based off of the log file. Oh, it just locked up on me. You get the idea. I'm sorry about that. All right. But essentially, you can go through and you can modify some of those settings, and then create your own spreadsheet with the reconstructed values in it. If you have questions, you can email me at rmaxwell2@radford.edu, and I can help you out through some of this, or come back to Field Week and we can run through this in a more advanced way in the future. I'll be posting a link to the example data set, and you can use that data set and use that to help you understand the formatting of the files, because I understand that's often a big challenge for running these programs. All right, take care and good luck.